Hi, good morning, guys. We're going to continue the earthquake engineering course online. Last time before we transferred to online, we started that example. We were almost done. Okay, we actually were done. Okay, there was just one thing. We had this frame, and it had the columns over here with EI, and then the beam or the floor over here had a rho EI stiffness. Okay, or moment of inertia rho I multiplied by the Young's modulus of E, okay? And we try to find the stiffness P equals KU. We wanted to find K here. How much is K, the stiffness regarding horizontal displacement, or this is side sway, okay, or a drift. This is called story drift. This U is the story drift, where the floor drifts due to a horizontal force P. Okay, so we did the derivation, we did the static condensation, we to eliminate thetas, theta 1 and theta 2, and that was a long process, but at the end, doing this, we ended up with that formula. When we substituted rho equal infinity, we found that K is equal to 24 EI divided by L cubed U, so K is 24 EI divided by L cubed, and we had two columns, so it's actually 12 EI divided by L cubed for each column. So this is an important conclusion, 12 EI divided by L cubed for each column. This is the stiffness that comes from each column, okay? If you have 100 column, you're just going to find 12 EI divided by L cubed for each column, and then you add them together. On the other hand, if rho is so small, that means that there is no interaction between the slab or the floor over here and the columns, okay? It will be, if you substitute rho here equals 0, okay, it's going to be, you're going to end up with 6 EI divided by L cubed divided by the two columns. That means you have 3 EI divided by L cubed for each column. That's K, okay? And here, this is equivalent to have a pinned column, okay, where there is no interaction between the floor or the roof or the slab over here. So either if the slab is so thick, okay, but there is no connection, okay, the rotation is not transferred from the column to the slab, that means that this is like a pinned connection, okay, and you're going to end up with 3 EI divided by L cubed, okay, as the stiffness of such column, where there is no interaction or there is no rigid connection between the column and the floor over here. So as a summary, simply K is 12 EI divided by L cubed for each column for the rigid floor, with rigid connection between the column and the slab or the floor. Or it's 3 EI divided by L cubed for pin and column, where there is no interaction between the column and the slab or the floor. If it's somewhere in between, okay, where you don't have a completely rigid floor, okay, it's going to be somewhere in between those two values, 12 EI divided by L cubed to 3 EI divided by L cubed, okay? Now, let's see an example that was in the textbook, okay, example 1.1. So in example 1.1, we have a small one-story building that is 20 by 30, okay? So when you have a look on the building from the top, okay, so this is the building over here. Okay, I hope you see the mouse, the movement of the mouse over here. So let me see if I can move you now. Okay, so anyway, let's go to select over here. It might be, yeah, I guess you see the mouse now, the mouse movement. So now if you have this is a top view of the building, so it's 20 by 30 feet. It's just supported, this area is supported by 4 columns here, W columns or W sections, okay, so they look like an I-beam. So those are W8 by 24, okay, those are the 4 columns. The IX of that column, if you took the steel structure course, you can, once you know the section, you know how to get its IX and IY, the moment of inertia in the X, the moment of inertia of the Y. So those are the values of the moment of inertia of those W8 by 24 sections. So we have those 4 columns to support this roof or floor, Okay, so the roof is supported by this truss. Okay, so this truss, we're going to assume that this truss, okay, as you see here, the height of this truss, normally it's so big. Okay, so the moment of inertia of this truss or roof truss will be very high compared to the moment of inertia of the column. So we can assume here that we have a rigid floor. So when we find the stiffness of the column is going to be 12 EI divided by L cubed, because we have a rigid floor, because the truss, the moment of inertia of the truss will be so big compared to the moment of inertia of the column. So this is what we have here, okay? And this building, okay, there is, to resist the horizontal force that comes from earthquake, for example, okay, we have a system, two systems. So this is the north-south direction, west-east, okay? So west, east, north, south. So if you have a look at front view of the building, okay, what we're gonna have, okay, side view here. So in the side view, okay, if you have a look from the side view, so in the north-south direction, okay, if there is a horizontal force applied, okay, in this direction, there is a frame. So there is this column here, and then this column over here. Okay, there are two of them, two frames. So one frame. There is a rigid connection between the column and the roof over here. Okay, so when there is a horizontal force, the columns will give the horizontal stiffness. There is a horizontal force over here. There will be a horizontal stiffness that comes from those columns. On the other hand, okay, if the wind or the earthquake or the horizontal force is applied from the other direction, okay, in this direction, okay, how will it be resisted? Actually, on the other direction here, if you have a front view here, okay, so you have the columns over here. In between the columns, we have those vertical bracing, okay. This is horizontal bracing in the, that you see on the plan view, but this is vertical bracing, so that when there is a horizontal force here applied, okay, in this direction, okay, the bracing, okay, will resist the horizontal force. Okay, the height of this floor is 12 feet, and then we have here the 30 and the 20 feet over here. So now those bracing members here in the vertical bracing, those vertical bracings, okay, are made out of steel. Everything here, the columns and this bracing are made out of steel. The bracing are made out of 1-inch diameter rods. Okay, so this is the section. This is a very small diameter, but this will do the job. Okay, usually bracing are made out of very small diameter rods. Okay, for small buildings like this. So what are we required to do over here? Okay, is to find the stiffness K against drift. So when there is a horizontal force in the top view on the floor system, applied on the floor system over here, a wind or earthquake loading, how much is the stiffness? Once in the north-south direction, if the force is applied from the south to the north in this direction, okay, can you see like this, okay? How much is the stiffness? In this case, the stiffness comes from the frame over here, or the other way, also the other thing that we want to find, if the horizontal force is applied from the west to east direction, west to east like this. So west to east, you're going to be, resisting, what's going to be resisting the horizontal force is those bracing as well as the columns. We're going to see the contribution of each of those parts, the vertical bracing as long as the columns. So now let's start with the north-south direction. When there is a horizontal force here applied in the north-south direction, the frame is going to drift with a value u. How much is k? P equals ku. How much is k? This is what we're looking for. Okay. So what's resisting the motion here? You have 1, 2 columns and another 2 columns. So you have 4 columns, and the column is bent about the x direction. Okay. So now k is going to be the summation, as we mentioned, assuming we have a rigid floor. Roof truss have very large stiffness compared to that of the column, so we're going to be assuming a rigid floor. We have k equal to the summation of 12 EI divided by L cubed for each column we have. The four columns are identical, so I can just multiply 4 multiplied by the EI divided by L cubed for each column. If the columns have different sections, you will just have to find 12 EI divided by L cubed for each column and then sum them together. So here we have 4 columns multiplied by 12. E, this is the moment of the modulus of elasticity of steel, 29,000 KSI. That's a constant value for steel. Multiplied by I. Which I? It's IX, because in the north-south direction, okay, north-south, this column is going to be bent about the X direction over here, okay? So IX, which is 82.8 inch power 4, divided by L cubed. The length of the column, this length is 12 feet. It was given over here, so this is 12 feet. Okay, it's 12 feet over here. So 12 feet, but the units that we are using here, we have KSI, and this is inch per 4. So I need to change feet to inches, so 12 feet multiplied by 12 inch per foot, and then all cubed. So K is going to be 35.58 kips per inch. So this is the stiffness in the north-south direction. Okay, you need 35.58 kips so that the frame drifts 1 inch in the north-south direction. Okay, what about the east-west direction? In the east-west direction, this is the force in the east-west direction, like this. Okay, what's going to be resisting? So this is a section over here. You have P, and this is the frame and the bracing over here. Okay, you apply P, the frame is going to drift with a displacement U like this, so it goes like this. So this is the dotted lines here represent the deformated shape, or the deformed shape, sorry. You have those spacings, they're going to move as well. So this spacing in green is going to go to this location. This spacing over here is going to go to that location. Okay, when you apply P, force P. Now, how much is U? If P equals KU, we can find, if we find K, that's the stiffness, okay? But now the displacement, what resisting the displacement U is the frame, the 4 columns, this 1, 2, 3, 4 columns, as well as the bracing. We have here a vertical bracing here, a vertical bracing here. So there are 2 of those frames. Can you see? This picture over here represents this frame over here, and then another frame over here, okay? The 2 columns, and there is vertical bracing in between, 2 columns and vertical bracing in between, okay? So how much is the stiffness? Actually, there are both of them, the columns and the bracing resisting the horizontal force or resisting the drift. So K is going to be the summation, K of the column plus K of the bracing, okay? So K of the column, as we learned earlier, we have 4 columns. So, and each one assuming a rigid floor as well, because we still have the truss on the upper floor, okay? So it's 12 EI divided by L cubed. So 4 columns multiplied by 12 EI divided by L cubed. 12 E is 29,000 KSI. I here, now this is bending about the Y direction, okay? It's going to drift like this, so it's bending about the Y direction, okay? So IY, 12.3 inch per 4, divided by the length of the column cubed, 12 feet, multiplied by 12 inch per foot cubed. So for the 4 columns, we have a stiffness of 8.52 kips per inch. That's small compared to that value that we have here. It's almost 1/4 of it, okay? Less even than 1/4 of it. That's why we needed to add the bracing, okay, to give more stiffness to the building, okay, because the moment of inertia of the columns about the Y direction here is so small for those sections, so we need to add more stiffness by adding those bracing over here to resist the horizontal force, okay, which comes from the earthquake, mainly the earthquake or the wind load, okay. Now for the bracing, okay, how much is the stiffness? Here, if we have a bracing, can you see here? This is the initial location of one of the bracings. Okay, it has a length L. It has an angle theta over here with the horizontal. Okay, once you apply a force P, okay, it's going to move to that dotted location. Okay, so it's going to move here from here, this point to that point, and this point is fixed to the foundation. Okay, so how much is P as function of U? P equals KU. Once we find K, this is the horizontal, okay, or this is the stiffness of the bracing. So how can we do this? We know a bracing is like a truss member. It can only resist the force in its direction, okay? So we want to find P in terms of U, but for the bracing member, it can only resist the force in its direction. So the force applied on the bracing, okay, if there is P over here, okay, there will be a larger force in the bracing, which is P divided by cosine theta. So P divided by cosine theta over here, because this angle is theta over here, okay. The component of B divided by cosine theta in this horizontal direction is P, okay. So if you analyze this P divided by cosine theta into two components, one in the horizontal direction, one in the vertical direction, we're going to have P, and then the other one over here, which is P divided by cosine theta multiplied by sine theta. So the component of the force in the direction of the truss or the bracing member is P divided by cosine theta. Okay, so now studying this truss in the axial direction, its axial direction, we know the force applied on it will be P divided by cosine theta. How much is the elongation? So the initial length is L, okay? If it rotates like this part is L, but then it will need to be elongated to reach the horizontal direction over here. So the point moves from this point to this point. So there is an elongation of this value here from this perpendicular direction to the end over here, okay, as we learned in structural analysis 2. That's why structural analysis 2 is a prerequisite for this course. We did this, we proved this for the truss members. So how much is this elongation? If this is U, we have this triangle over here, okay. If this angle here is theta, so this angle here, okay, this angle here is theta. This is 90, this is theta, this is 90 minus theta. So if this is U, then this elongation is U divided by cosine theta. Now, simply applying the Young's modulus is equal to the stress divided by the strain. The stress is the force, which is B divided by cosine theta divided by the area. The strain is the elongation, which is U divided by cosine theta divided by the initial length, which is L. So now we can put P in terms of U, so we're going to move P to one side of the equation and U to the other side of the equation. So we're going to find that P is equal to EA divided by L and cosine square theta U multiplied by U, okay? So now, okay, that means P is equal to this value, K, multiplied by U. So that means that the stiffness of a bracing is EA divided by L multiplied by cosine square theta. How many bracings do we have? As you see here, the bracing between one frame, you have 1, 2 members, and then there is another bracing over here, so you have overall 4 members. But when you apply a P over here, one of those members are going to be under compression. For example, this one is going to be under compression, the other one will be under tension. So we have 4 bracing members, that's correct, okay? But 2 of them will be under compression and the other 2 will be under tension. Those 2 that will be under compression, what will happen is they will buckle way before the tension members, the members under tension, reach their strength. So actually those bracing members that are under compression won't be able to provide this force, okay, as the tension members. They will buckle way before providing this stiffness, okay? So actually we're going to assume just we have 2 bracing members overall, only the tension members. The compression are not going to be counted, okay? So K bracing is 2 bracings multiplied by the stiffness of a bracing, which we just derived over here. It's EA divided by L multiplied by cosine square theta. So EA divided by L multiplied by cosine square theta. How much is L? The length of the bracing. The bracing is inclined like this. The horizontal distance is 20. The vertical distance here is 12. So the length is square root 20 squared plus 12 squared. So it's 23.3 feet. Cosine theta, we need cosine theta over here to find the K for the bracing. So cosine theta, this is theta, cosine theta is going to be the 12 divided by L, which is 23.3. So cosine theta is 0.8575. Now we can find K for the bracing system. We have 2 bracings multiplied by E, which is 29 times 10 to the power 3 KSI. A, the area of the bracing. We have a rod with a diameter of 1 inch. The area is pi d squared divided by 4. So pi multiplied by the diameter of the bracing, 1 inch squared divided by 4. So that's the area of the bracing, multiplied by cosine square theta, divided by L, which is 23.3 feet, multiplied by 12 inch per foot. So the K for the bracing is 119.6 kips per inch. That's very big compared to the stiffness that we got from the columns. So over here, the total stiffness that comes from the column is 8.52, that comes from the bracing is 119.6, so overall the stiffness is 128.19 kips per inch. Now, if you compare those two numbers to each other, the K that comes from the bracing is 119, while that comes which comes from the columns is 8.52. Okay, so the columns contribution is about just 7%. Okay, it's a common practice here. Okay, in the weak direction of the columns, if you have bracing, that you neglect the effect of the columns. Okay, you just neglect this 8.52. You're neglecting 7%. Is that wrong? It's conservative. Neglecting this, you're more conservative. You're just assuming that you have a less stiffness. Okay, you have less stiffness. Okay, so you're on the safer side over here. If you neglect this, okay, you're not, you know, you're actually more conservative over here. So actually, it's a common practice when you have racing, you just find the stiffness of the bracing, which is 119.6 kips per inch, and neglect this part. Okay, if you want to calculate it, that's fine, but if you want to eliminate this part or neglect it, you're just losing about 7, or you have 7% error, and that error is on the safe side. You're more conservative, not less conservative. Okay, so that's a problem here on how to calculate the stiffness regarding horizontal forces in braced frames and non-braced frames. Okay, so this is a very nice example on calculating K. Now we're going to have another example. Okay, let's jump to that example before we cover this part. So I'm going to skip 2 pages like this and have another example here. Let's say we have a building or a frame. It's fixed. The column here is fixed. Okay, there is this floor. Okay, it's a rigid floor, and we want to find the stiffness of the drift of that floor. This floor is supported by 1, 2, 3 columns over here and 2 columns to the top, and the end of the columns at the top is fixed. Okay, somehow. Okay, they are fixed to somehow. Okay, so they cannot move. How much is the stiffness here? So for this floor to move, the end of this column, the end of all those 5 columns, 1, 2, 3, 4, 5. Okay, the end of them will move. Okay, if each column has EI and length, okay, this is L2. Those there has different lengths as L1, L2, L3, and the moment of inertia are not equal. So simply the stiffness is going to be the summation of those all EI, all 12 EI divided by L cubed if we have rigid floor, or 3 EI divided by L cubed if we have bent convection. Here we have rigid floor, so you just need to sum 12 EI divided by L cubed for each column. You need just to use the correct I and L for each column. So for example, column 1 you have EI1, L1. For column 2 you have EI2 and L2. For column 3 you have EI2 and L1, and so on. Okay, so you just sum up those values and you find the stiffness, okay, for the drift due to a horizontal load that might come from an earthquake. Okay, so now we're going to start the topic, or the important, or the major part of the course, which is the dynamic analysis of structures. What we learned in structure analysis 1, structure analysis 2, is doing a static analysis where you solve P equals KU. Okay, so for a static equation, okay, we had P equals KU. K is the stiffness of structure. You learned how to do this in structure analysis 1. We reviewed this as well here to do static condensation, to find P in terms of U and eliminating theta 1, theta 2 over here. So if we have a frame like this, you just find P equals KU. Okay? And you learned that for rigid frames, K is equal to the summation of 12 EI divided by L cubed for fixed column, or 3 EI for L cubed for pinned columns. Okay, but on the other hand, okay, this is static analysis. Okay, static equation of equilibrium. On the other hand, okay, what we're going to be doing in this course, an earthquake loading is not a static force. It's a dynamic force, and not only a dynamic force, it's a dynamic force that changes so rapidly. Okay, it changes so rapidly. Okay, seismic loads. Wind loads, we don't assume that wind loads are dynamic load, because yes, they are changing, but the rate that they change by is slow. But dynamic analysis for seismic loads is so important, because the load, okay, when you have an earthquake, the entire duration of the earthquake might be 5 seconds, for example, but during that 5 seconds, okay, the earth or the ground, okay, it moves back and forth maybe 1,000 times, okay? So the load is changing so rapidly, and we need to do a dynamic analysis. So how does the dynamic analysis compare to the static analysis? The static analysis, you just have P equals KU, okay? We're gonna model this, okay? There is a very famous model, okay, that is called the mass spring system. So we're going to assume here, okay, or not assume, we're going to model this or look to this frame as if, okay, it's so equivalent. You have a mass over here, the mass of the floor, or the mass of the building is lumped. We're going to assume that the mass of the building is lumped. The most of the mass of the building is at the floor over here. When you apply P, it's going to move a distance U. How much is that distance U? There is a resistance that comes from the columns K, right? So it is as if you have a mass over here. It's connected with a spring, okay, that has stiffness K. You apply force P, so it's going to move a distance U, and P equals KU. When you put P over here, there will be a force that comes from the spring in the opposite direction that is equal to KU. The more U is, okay, the more this force will be, okay? So at the end, it will move until it becomes in equilibrium, and P equals KU. So this is, this equation for this frame is equivalent to just the mass here, and it's connected with a spring, okay? It's resisted by a spring over here. You apply the force P, okay? So always P equals KU. KU is the force applied by the spring on the mass over here. So you apply an external force P, the spring apply another internal force, KU, in the opposite direction. They are in equilibrium, P equals KU, okay? So now, for dynamic analysis, okay, we have the same system, which this system represents the frame that we showed earlier. So this system is representing, okay, the frame over here. This frame can be modeled, okay, as if it's just a mass, okay, the mass of the rigid floor, and this is the force applied on it, the horizontal force. You apply a force, there will be a displacement U. But now, if this force is not just the constant force as we had over here, P, so in the previous part over here, P was constant value, and it's going to be equal to that KU, constant value, okay? And that's it, that's the static equation. But for dynamic analysis, P is not constant, P is changing with time, so P is function of T. So since P is function of T, U also is going to be function of T, okay? So how much is U as function of T? That's what we actually, okay, is the target of this course. How much is the displacement as function of time if we know the force as a function of time, okay? Applied on our frame or structure over here, okay? So now we know it's connected by spring, okay? So if this moves a distance U, there will be a force in the spring that is equal to KU. So you have P, you're going to have a force in the opposite direction that is equal to KU. But those are not in equilibrium with each other. Why? Because P changes so fastly. As you know from Newton's second law, the force is equal to the mass multiplied by the acceleration, okay? So there is another force applied on the system if the force applied, okay, is changing rapidly, okay, there is another force called the inertia force, which is equal to mu double dot. What does this mean? Let's say, okay, you're sitting in your car, okay, the car is not moving, okay, and at once, okay, you press the gas so hardly, okay, you move from 0, okay, to let's say 40 miles an hour in just 3 seconds, okay? You have a cup of coffee on your dashboard, okay? What will happen to this cup of coffee? Definitely it will get spilled, it will move back, the car is moving forward, okay? With this huge acceleration, the cup of coffee will move backward, okay? We learned in statics, if some object moves, that means that there is a force applied on it. So why did the cup of coffee, okay, move backward? That means that there is a force that is applied backward on this cup of coffee, okay? How much is that force, okay? As you see, the car is moving forward, this cup of coffee is moving backwards, okay? Now, let's say the same example that we did, the car is standing still, and then you press the gas, okay? But instead of pressing the gas so hardly as you did the last time, you're applying, or yeah, you're pressing the gas pedal so slowly, okay? You're going from 0 to 2, 3 miles an hour in 5, 6 seconds. Maybe the cup of coffee will not get spilled. It will not move in this way, okay? You're still gonna move the car until you reach 40 miles an hour, but the rate or the acceleration is so slow. The cup of coffee will not get spilled. It's not gonna move backward. That means that the force that is applied backward on this cup of coffee depends on the acceleration, okay? The acceleration, the rate of change of velocity, as the acceleration increases, okay, the force, the backward force that is applied on this cup of coffee increases. This force that is applied on this cup of coffee is called the inertia force. So here, when you apply a force here, P, that is changing so rapidly, U is going to change with a high acceleration. This object will move with a high acceleration U. There will be some inertia force that is function of the acceleration, U double dot. U double dot, so what's double dot here? It's d2u by dt squared. Okay, let me hide this here. This is, so m d2u by dt squared. Okay, this is called the inertia force. Okay, so as you see here in equilibrium, okay, F equal ma, the total force equals mu double dot. The total force that is applied on the object, it's P minus Ku. So this inertia force comes from the equilibrium here from Newton's second law. So P, the total force P minus Ku equals mu double dot. Mu double dot is the inertia force, okay? The summation of all three of them, P minus Ku minus mu double dot, has to be 0. Or P minus Ku equals mu double dot. So now I'm going to move P to one side of the equation. So we're going to have mu double dot plus K U equals P of T. P is the force applied that changes with the time. T changes with the time as well. So M multiplied by the second derivative of the displacement plus K multiplied by the displacement, that is function of the time, is equal to the P, the force applied, which is function of the time. So this is the equation that we need to solve. So for static equilibrium, it was just Ku equal P. But now for an object that is moving suddenly or rapidly, okay, the equation that we need to solve is mu double dot plus Ku equals P, okay? This is the equation that we want to solve. We want to find U. Exactly as we did in structure analysis 1, you had a structure and you wanted to find the displacement. Once you find the displacement, you find the internal forces. So here also we need to find the displacement, and once we find the displacement, we can find the internal forces. But the displacement is function of time. The displacement is changing with time because the force is changing with time. We want to get this from this equation. This is called the general undamped equation of motion. This is the equation of motion, okay, that we want to solve, okay? So m is the mass, okay, the mass of the structure or the mass of the floor, okay? K is the stiffness, so that's why we spent some time at the beginning understanding the concept of the stiffness regarding horizontal force, and we learned how to calculate this. So K is the stiffness against the movement U, okay? And our target here is to calculate U, okay? Once you find U, you can find the internal forces from the, slope deflection equation or the stiffness method, okay? So now the equation, this equation, let's write it like this. It's mu double dot, which is d2u by dt squared, okay? So u dot is du by dt, u double dot is d2u by dt squared. So I hope you understand this notation now, okay? U dot is du by dt, u double dot is d2u by dt squared, plus ku equals p, okay? We want to solve this equation. So what we're going to be doing throughout the lectures is we're going to be solving this equation again and again with different conditions, different forces and so on, okay? So we're going to start with the easiest thing that we have here to solve this equation. We're going to assume the P equals 0. There is no force. P of t is equal 0. We only have m d2u by dt squared plus ku equals 0, okay? So putting P equals 0, that means there is no force. So this equation of motion, okay, we're going to name this unforced, okay, because there is no force. So it's unforced or free vibration. There is no force that goes in the vibration over here. Unforced free vibration, okay? So how do you solve this differential equation? As you see, this is a differential equation, mu double dot plus ku equals 0. It's a differential equation because here you have differentiation with respect to the time, double differentiation with respect, the second derivative with respect to the time. So how to solve this? You assume that u as function of time is e power lambda t, and then you substitute here u double dot, the second derivative of e power lambda t, it's going to be lambda squared e power lambda t. So m lambda squared e power lambda t plus k. U is assumed as e power lambda t equals 0. You can cancel e power lambda t, okay, or divide the entire equation by e power lambda t, so you're going to end up by m lambda squared plus k equals 0. That's called the characteristic equation. Now, how much is lambda that satisfies this equation? So lambda squared is equal to negative k divided by m. So lambda is positive or negative square root k over m multiplied by I. What's I? It's the square root of negative 1. Here you have negative, so square root negative 1 is I, the imaginary number I. Okay? So this is the two solutions. Okay? You can only have free vibration. This equation that you assume that u as a function of t is e power lambda t. That's correct only if lambda is equal to plus or minus. Okay? Let me change the pointer over here. So this equation is only valid. U is going to be e power lambda t only if lambda is equal to positive or negative I multiplied by square root k over m. Okay? That value, square root k over m, is going to be a very, very, very important value for structural analysis, for dynamic analysis, for seismic loading, for earthquake loading. We're going to call this value square root k over m, omega n. Okay? Omega n is the natural frequency of the structure. Why is it called the natural frequency of the structure? This is why we give it the notation here of the subscript n. Omega is a frequency, so it's the natural frequency of the structure. We're going to know why it's named natural frequency, okay, just in a moment, okay? So now lambda is equal to plus or minus I, the imaginary number I, multiplied by square root k over m. Now we are saying square root k over m is called omega n, the natural frequency, okay? So u of t can be e power I omega nt or e power negative I omega nt, multiplied by some constant, okay? Or generally it can be a linear combination of the two solutions. So if u of t is this linear combination of the two solutions that we found over here, it will still satisfy the equation, the differential equation that we had earlier, okay? But from Euler's formula, this is the Euler formula as you learned in math, you can substitute e power I omega nt e power negative I omega nt and put cosine omega nt and sine omega nt from those Euler's formula. Doing so, we will get that u of t, instead here of having this exponential function with this imaginary power, okay? No, you can substitute this with cosine and sine, so u of t will be two new constants, okay? A cosine omega nt, okay, as you see here, cosine theta and I theta, so cosine omega nt and b sine omega nt. So this is the displacement as function of time. It's a cosine omega nt and b sine plus b sine omega nt. What are a and b? Those are constants. How much are those constants? Until this moment, we don't know how much are those constants. They are indeterminate constants until this moment. Okay? So the solution here is a linear, okay, combination of those two solutions. A cosine omega nt and b sine omega nt. Okay? Let's plot those two. Okay? If we plot the first one, a cosine omega nt, it's a cyclic harmonic force like this, okay, that repeats each, when omega nt is 2 pi, okay, once omega nt, okay, a function, a cosine function repeats every 2 pi. So cosine 0, cosine 2 pi and 4 pi and so on repeats. They are equal to 1. Okay, so this function repeats every 2 pi. So this function is going to repeat once omega nt is equal to 2 pi. So it's cyclic, okay, when the time becomes every 2 pi over omega n. Okay, so that's the, 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 as you see here, omega a cosine omega nt. Okay, so this is u of t, the first part of the equation, a cosine omega nt. It's a cyclic function over here, and one complete cycles will take a time that is equal to 2 pi divided by omega nt. So we call this the period. This is the natural period. The structure will be oscillating. The displacement, okay, u, is changing from positive a to negative a. Okay, positive a to negative a. There is an oscillation, and the period of oscillation is 2 pi divided by omega n. That means that the frequency of the oscillation is omega n. That's why we called omega n is the natural frequency of that structure. That structure, if it's vibrating under free force, no forces applied, it's going to vibrate with a frequency equals to omega n, or a period that is equal to 2 pi divided by omega n. Okay, that's why we called here omega n as the natural frequency. Okay, everyone, I hope everyone understand why we call omega n here the natural frequency of the structure. This is the vibration, okay, or the frequency of the vibration, and the natural period Tn is 2 pi divided by omega n. So here, once you know omega n, you can find Tn. This is the period. Or once you know Tn, you can find omega n. So I can represent the natural frequency or the natural period, you know, the structure. I can use any of those two quantities, Tn or omega n. Okay? So this is the frequency. This is the first equation here. A cosine, or the first part of the equation, A cosine omega nt. What about B sine omega nt? It's again an oscillating or harmonic function. It has the same period, 2 pi divided by omega n, but instead of starting with the value a, no, it starts with 0 and then oscillates to b, and then go back to 0, b, negative b, 0, b, 0, negative b, 0, and so on. Okay, so it's an oscillating function, okay, with the same period or the same frequency as the first one over here, but they are out of phase. What does this mean, out of phase? When the first one, the cosine omega nt, has its maximum amplitude, the sine has 0. When the sine function is the maximum, this one is 0. Okay, so they are oscillating with the same exact frequency, but they are out of phase. They are not oscillating with the same, you know, and they don't reach their amplitude at the same exact time. Okay, they're out of phase here. Okay, they are not out of phase. Okay, so that means that the period of the movement is, you know, since you have two movements that have the same frequency, so the period of the movement is the same here, Tn, which is 2 pi divided by omega n. This is the natural period. Okay, so and now you need to know that omega n is square root k over m. You need to memorize this. This is so important. Omega n, the natural frequency, is square root k over m. K is the stiffness. Again, it's the motion that you learned how to calculate this from structure analysis 1, structure analysis 2, and you know what we did at the beginning of the semester. And m is the mass of the floor or the building. Okay, so square root k over m, that's going to be, you know, the natural frequency over here. If you sum the two together, okay, it's going to be a function, okay, a cyclic function, but it starts with a and then it increases, okay, and then decreases and so on. So for cosine, it starts with a, but then it decreases, okay, the maximum is a. Here, this one, it starts with 0 and increases. So when you add them together, okay, at a here, it will not go horizontal. It go horizontal for cosine, but now you're adding this one, which increases a little bit. So here, when you add them together, it starts from a, increases, and then it's going to decrease, and then it will repeat each Tn, which is 2 pi divided by omega n. So this is how the displacement will look like. It's a cyclic displacement, okay, that repeats every 2 pi divided by omega n. That's the period, okay? So now, how much is those two constants, a and b, okay? So how to find those? Those can be calculated from the boundary conditions. So we have that structure. Okay, let's go up. Okay, uh, it's vibrating. Okay, under no forces. That's free vibration. Okay, so if you go up all the way, okay, just to remember this, okay, we have that structure. Okay, we have that structure. It's vibrating. There is no force. Okay, so if there is no force, how will it vibrate? It might vibrate maybe due to an initial condition. Okay, what does this mean? Okay, at the beginning of the motion, someone pulled the truss, or sorry, pulled the frame to the side like this with an initial displacement u naught. Okay, and then it left. You release this displacement. Okay, so the frame will go back and vibrate a little bit. Okay, and keep vibrating. So there might be an initial displacement here to start the motion, or there might be an initial velocity. What does this mean? Maybe the frame starts from zero displacement, but it's moving with an initial velocity, u dot naught. Why? What's u dot naught? U dot is the velocity, the du by dt. Node, okay, is the initial. Okay, so u node is the initial displacement that can be applied to on this frame, and u dot node is the initial velocity that can be applied on this frame. Okay, so now to find a and b, the two constants, those can be found, okay, from the initial conditions or the boundary conditions. So at time t, okay, the initial condition, there might be some initial displacement u node. Okay, so we're gonna put we so far we found that u of t, the displacement, okay, is a cosine omega nt plus b sine omega nt. When we put t equals 0, that's the initial condition. So t equals 0, when t equals 0, the displacement will be 0. So sorry, u naught. So u naught is equal to a cosine 0. Cosine 0 is 1 plus b sine 0, which is 0. So actually a will be u naught. So the constant a is the initial displacement. Okay. On the other hand, okay, du by dt, we're going to write it as u dot t, okay, u dot, okay. So at t equals 0, the initial velocity u dot of 0 is u dot node, okay, the initial velocity that the structure can start vibrating with. So u of t, we know u of t, we found u of t is a cosine omega nt plus b sine omega nt. How much is, if this is the displacement, how much is the velocity? The velocity is the derivative of the displacement. So let's differentiate this equation with respect to t to find the velocity, which is u dot of t. Okay, so u dot of t is just the differentiation of that equation over here. So it's going to be a cosine omega nt. You know the differentiation of cosine theta, or yeah, cosine a theta or something constant multiplied by theta is the negative sign that function multiplied by the constant here. So negative a goes omega n, the sine omega nt, and then the differentiation of sine omega nt is cosine omega nt multiplied by omega n. So b omega n cosine omega nt. So this is simply differentiating those two terms with respect to the time. Okay, so now the velocity of the vibration at any time t, it comes from this equation over here. What about the initial, when t is equal to 0? How much is the velocity of the vibration? That's the initial velocity. If we know it, we can just substitute it over here. The initial velocity is u dot node. U dot is the velocity, node means the initial velocity. So at t equals 0, u dot node is equal to negative a cosine omega n sine 0, which is 0, plus b omega n cosine 0, which is 1. So that means that omega u dot node is equal to b omega n. That means that b is u dot node divided by omega n. Substituting those two constants a and b that we found into the equation, so u of t, the displacement at any time, okay, under free vibration for that structure, that will be can be calculated from this equation. U naught, the initial displacement, multiplied by cosine omega nt plus u dot node divided by omega n multiplied by sine omega nt. So this is the general solution to the equation of motion. Generally, you might have an initial displacement, okay, and the initial velocity is 0. If the initial velocity is 0, this term is going to cancel, and you only have u node cosine omega n t. Or for example, you can have an initial velocity, but the initial displacement is 0. You have a structure, you give an initial velocity, okay, and then it's going to keep vibrating until this initial velocity. That means that this term is going to cancel. You only have the second term over here. Or you can apply an initial displacement plus some initial velocity. You're going to have both contributions. So this contribution comes from the initial velocity displacement. This contribution comes from the initial velocity, okay? And then you sum both together, okay? So this is the general solution for the equation of motion. Now, we said if you have those two contributions like this, okay, that if we plot this function, okay, it will look like this. It starts with A and then increases and then decreases and have this cyclic equation. What's the maximum amplitude here? It's going to be some value that is larger than A. How much is that maximum amplitude? We want, to write the equation for this, okay? So to find the maximum amplitude here, okay, what's the maximum amplitude of the motion? You have u as function of t. You want to find u maximum. U maximum will happen when du by dt is equal to 0, okay? When will du by dt be equal to 0? We want to find that time. We're going to name that time tau, okay? When will the velocity be 0, okay? The velocity of the vibration, that will give the maximum amplitude. So du by dt, we already know this is u of t, so du by dt is the derivative, so it's going to be negative u node omega n sine omega nt plus the derivative of this part is going to be u dot node multiplied by cosine omega nt. So this is the derivative, the velocity at any time, okay? We want to put du by dt, okay, equals 0. What's the time here that this value will be equal to 0? The velocity here will be 0. So putting the velocity equal to 0, and the time is going to be that time where the velocity reaches its maximum value. We're saying this time is called tau, okay? So now you're going to have 0 equal negative u node omega n sine omega n tau plus u dot node cosine omega n tau. Let's move this term to this side of the equation. So u node omega n sine omega n tau is u dot node equal to u dot node cosine omega n tau. As you see here, you have the sine and cosine of the same function, so dividing both of them by each other, sine divided by cosine, so that's tan omega n tau equals to u dot node divided by u node omega n. So that represents a triangle over here, okay? The tan of the function of the angle, tan omega n tau, this is omega n tau, is equal to the opposite divided by the adjacent, okay? U dot node and then u node omega n. The diagonal over here is going to be square root the two sides, okay? U dot node squared plus u node omega n squared, square root of that, okay? So that's tan omega n tau. What about sine omega n tau? So now this is the angle omega n tau. Sine is going to be this opposite u dot node divided by the diagonal. So u dot node divided by the diagonal over here. Cosine omega n tau is going to be the adjacent u dot node omega n divided by the diagonal value over here. So this is sine omega n tau and cosine omega n tau. U of t is equal to u node cosine omega nt plus u dot node divided by omega n sine omega nt. This t, okay, u of t will be maximum when t is equal to tau. So u of tau, this is the maximum amplitude, is going to be u node cosine omega nt, cosine omega n tau, cosine omega n tau. When t is equal to tau, this becomes cosine omega n tau. Cosine omega n tau comes from this equation, so I put cosine omega n tau plus u dot node divided by omega n over here multiplied by sine omega n tau. Sine omega n tau comes from here, so I put them over here, and then you take this as common factors, the square root u dot node u dot node squared plus u node omega n squared. So I take this as a common factor from the two terms over here. You're going to have here u node squared omega n plus u dot node squared divided by omega n, okay? This second term over here, I'm going to multiply it by omega n, okay, in the numerator and denominator, okay? So we're going to have u dot node omega, u dot node squared omega n divided by omega n squared, okay? So why is this? Because when we have omega n here as a common factor, I'm going to take this omega n as a common factor, okay? So here you have, I want to have this term here as well, okay? So here you have u dot node, okay? So multiplying by omega n and omega n here, we're going to have u dot node squared, okay? This one cancels with this one, and then omega n, I'm going to take this as a common factor, okay? So this is the, you know, simplifying this, we're going to have 1 divided by omega n multiplied by square root u dot node squared plus u node omega n squared. This is the maximum displacement, okay? I hope you get how to simplify this one. Let's explain more how to simplify this. Here you have, I want this term here to be exactly like this one. Over here you have u node squared omega n. Here you have u node omega n squared. So we need to have omega n squared over here for that term to look exactly like this term. So if I have omega n squared here, it's going to be divided by omega n, okay? So imagine you have omega n squared divided by omega n. Now this term looks exactly like this one, but that is divided by omega n here. And then this term over here, you have u dot node squared divided by omega n. Here you have u dot node squared only, so I want to cancel this omega n. When I multiply by omega n and divide by omega n, I'm going to have omega n and omega n over here. Those are going to cancel, and we're going to have omega n in the lower part over here, and also we have omega n here in the lower part, so I'm going to take this as common factor. That's why we have 1 divided by omega n over here. And then this term is going to look exactly like this one, but now you have square root over here, and you don't have square root over here, so the square root goes here, okay? Like 2 divided by square root 2 is square root 2, okay? So it's 2 divided by square root 2. Imagine it's something divided by square root of that something, so it's the square root of that thing, okay? So that's the maximum displacement over here, okay? So now if you look to those two terms, actually it's square root a squared plus b squared. It's the square root of the squared of the two constants, okay? That's the maximum or the amplitude of the displacement. Now, another thing, okay, that we want to find, okay, is the energy during that vibration. We have that frame, okay, or that mass representing the frame. It's vibrating like this, okay? When it's vibrating, there is an energy. How much is the energy during that vibration? Okay, so at any moment, the energy is simply, it comes from the kinetic energy, okay, that comes from the velocity of the vibration, okay, and a potential energy. Actually, we're not going to call that a potential energy, we're going to call that the strain energy that comes from the spring. So actually what we have is when you have a spring, okay, you know the energy or the work is equal to the force multiplied by the displacement, okay? That's the work or the energy, okay? So now if we go here to find the energy during the motion, we have the kinetic energy and the strain energy. So what's the strain energy? Let's explain this. You have this spring, okay? You apply a force P, okay? So there is another force here in the spring that is equal to Ku, okay? So how much is, so this moves a distance U, okay? So the energy is equal to 1/2 the displacement multiplied by the force Ku. So the energy here is going to be 1/2, okay? 1/2 K multiplied by U squared. So that's called the strain energy, the force multiplied by the distance, the force in the spring multiplied by the elongation of that spring, okay? So 1/2 Ku squared. What about the kinetic energy? You, from physics, you know the kinetic energy is 1/2 mv squared. V here, V is the velocity, so we name this u dot, okay? So this is the notation that we are using for the velocity, 1/2 mu dot squared. So the energy, the total energy at any moment is equal to the kinetic energy plus the strain energy. The kinetic energy is 1/2 mu double dot plus 1/2 ku squared, okay? U, we know U, okay? U at any moment as function of time is U naught cosine omega nt plus U dot node divided by omega n sine omega nt. You square this and put it over here. And then U dot node, okay? You have the equation, you derive this, okay? And then square it multiplied by m, by 1/2 m. You put it over here, okay? You're gonna end up, okay, if you do the simplification, okay, knowing that also to be able to reach that formula, you need to know that, you know, omega n is square root k over m, okay? Knowing this, you're gonna end up that the total energy, okay, during the vibration is equal to 1/2 k. K is the stiffness of the spring, it's a constant value, but multiplied by u node squared. U node is the displacement, the initial displacement. That's a constant value as well. Plus 1/2 m, the mass of the structure, which is constant, multiplied by u dot node squared, which is constant. That means that the total energy is constant throughout the vibration. Okay, it's not changing. The energy is not changing. Okay, the frame or the structure will be vibrating with constant energy. The energy is not dissipated. Okay. There is no dissipation for the energy, okay? What does this mean? It means that this structure will oscillate infinitely, okay? It will keep oscillating till the end of time, okay? Is that logical? Definitely it's not, okay? When you have a frame, okay, you apply an initial displacement, it will keep vibrating back and forth, okay? Yeah, forward and backward, okay? Until, okay, maybe 10 seconds, 20 seconds, and every time each, you know, oscillation, each cycle, the displacement will decrease a little bit, exactly like a pendulum. Imagine you have a pendulum, okay? You apply an initial displacement on the pendulum, and then you leave it. It's going to oscillate, okay, back and forth, but it's not going to do that infinitely, okay? Maybe 10 seconds, 20 seconds, 30 seconds, okay? Until it stop moving, okay? What does this mean? To stop moving, it means that the energy is getting dissipated. When you have this pendulum, you apply, imagine you have a pendulum, let me draw this, okay? You have a pendulum like this, okay? And then you apply an initial displacement, and then you leave it. It's gonna oscillate like this, okay? But each time, it's gonna, you know, the oscillation is gonna decrease until it, you know, stands still over here. So during that oscillation, it has an energy, okay? And then the energy is decreasing, decreasing, decreasing until at the end, the energy, the entire energy is dissipated, and there is no energy, it stops, okay? So this is the logic, this is what happens in real life. Exactly now, if you have a frame, so this is similar to a frame like this, okay? And you apply a displacement, u, okay? It will keep, this frame will keep oscillating back and forth, okay? Imagine the frame is oscillating to this side and then to this side, okay? But each time, okay, the displacement should decrease. But this is not what we're getting over here. We're getting that, no, this oscillation will happen infinitely, okay? So we are missing something, okay? What is that thing that we are missing? It's called the damping, viscous damping, okay? So what's the viscous damping in structures? This can be classified into two parts, frictional damping and viscous damping. This is what we're going to be using, the viscous damping, okay? The viscous damping is a damping that increases with the increase of velocity. So what does this mean? Let's say here you have a car, okay? The viscous damping, okay? The car is moving with a velocity, okay? The more the velocity is, there is air surrounding this car or structure, okay? The more the velocity, the more the resistance of the air will be, okay? So the viscous damping increases, okay, with the increase of the velocity. So when you have the frame, okay, when the frame is oscillating with a high velocity, there will be high frictional force that resists this movement. Okay, so as you see, this is another force that will be applied on the structure that we didn't put in our equation of equilibrium. So there is a force that is function of the velocity. Now what do we call the velocity, or the notation we put for the velocity is u dot du by dt. Okay, so so there is a force that is function of the velocity. This force is going to be equal to c u dot. Okay, it's function of the velocity. So it's a constant c called the damping coefficient multiplied by the velocity. The more the velocity, the more the damping force will be. So now the equation, we need to change our equation of motion a little bit. Okay, initially we had mu double dot plus ku equal p. That's the equation that we had. But this didn't include any damping force. Now we need to add this damping force, cu dot. Okay, so now mu double dot plus cu dot plus ku is equal to 0. So this force is resisting the motion. Okay, and it's function of the velocity. And c is called the damping coefficient. Okay, so c is the damping coefficient. Now for free vibration, we want to solve the same exact equation again. Mu double dot, but we adding this term cu dot plus ku equals 0. This is free vibration, but free damped vibration. The other equation without this term cu dot, okay, was named the free undamped motion, equation of motion. Here we have the free damped equation of motion, mu double dot plus cu dot plus ku equals 0. So the same structure here, okay, without damping, okay, we found that omega n, this structure has an omega n that is equal to square root k over m. If it vibrates freely, okay, with no damping, the frequency of the vibration would be omega n, which is square root k over m. So actually omega n square root k over m, so squaring both sides of the equation, we can say that k is equal to omega n squared multiplied by m. So that's k. Okay, so I will remove k over here and put m omega n squared. So we have m u double dot plus cu dot plus m omega n squared u is equal to 0. I will divide the entire equation by the mass, so this becomes u double dot plus c divided by m u dot plus omega n squared u. Okay, now for this factor c over m, okay, I will introduce a new factor called zeta. Zeta is the damping ratio. Okay, zeta is c over m over here, but divided by 2 omega n. So c over m is going to be 2 zeta omega n. Okay, so I will remove c. C is the damping coefficient. Zeta is the damping ratio. Okay, so those are different. Okay, c is damping coefficient. Zeta is damping ratio. Okay, so I will remove c over m and put 2 zeta omega n. So the equation now is u double dot plus 2 zeta omega n u dot plus omega n squared u equals 0. Okay, we need to find the solution here. How much is u, the displacement as function of time? Okay, so again, as we did for the free undamped equation of motion, we assume that u of t is equal to e bar lambda t. We're doing the same thing over here again. So u double dot, the derivative of e bar lambda squared, the second derivative will be lambda squared multiplied by e bar lambda t. So lambda squared multiplied by e bar lambda t plus 2 zeta omega n u dot, the derivative will be lambda e bar lambda t, so lambda multiplied by e bar lambda t plus omega n squared u, which is e bar lambda t, equals 0. I'm just going to divide the entire equation by e bar lambda t, so I got rid of e bar lambda t when I substituted over here. So how much is lambda that satisfies this equation? As you see, this is a quadratic equation in lambda. Okay, so you have lambda squared multiplied by this factor multiplied by lambda plus a factor with omega n squared, okay, equals 0, constant. So you know the solution for a quadratic equation. If you have a quadratic equation that looks like this, ax squared plus bx plus c equals 0, this has two solutions, which is negative b plus minus square root b squared minus 4ac divided by 2a. Okay, so here instead of x we have lambda, so there are two solutions for lambda. Okay, there are negative b here, so negative this term, so negative 2 zeta or omega n plus or minus square root b squared, so b squared, this is b, 2 zeta omega n squared minus 4 a which is 1, c, which is omega n squared, divided by 2, a is 1 over here. So those are the two solutions. As you see here, we have 2 squared and we have 4 over here, so I can take 2 as a common factor. And here we have 2, so I'm going to cancel this 2 with those 2's over here. So I'm going to have negative zeta omega n plus or minus. We have omega n squared over here. I can take that as common factor, so we have omega n squared, getting it outside the square root, so it's omega n over here, and then multiplied by square root zeta squared minus 1. So the two solutions is negative zeta omega n plus or minus omega n multiplied by square root of that. So instead of having zeta squared minus 1, I'm going to have it 1 minus zeta squared. So this is multiplying by negative 1. So the square root negative 1 is I. So it's omega n I multiplied by square root 1 minus zeta squared. Okay? So those are the two solutions. That means that u of t can be a linear combination of the two solutions. The two solutions is positive or negative over here. So we have e, the solution was e power lambda t. So e power lambda 1 t plus e power lambda 2 t. Okay? So c1 multiplied by e power lambda 1. Lambda 1 is negative zeta omega n, and positive this value t, plus c2 e power lambda 2. Lambda 2 is where you have a negative value over here, multiplied by t over here. Okay? So that's u of t. As you see over here, we have e power negative zeta omega n as a common factor here. Okay? So I'm going to take e power negative zeta omega n common factor and then multiply by the rest over here. C1 e power negative power I omega n multiplied by square root 1 minus zeta squared t, and then the other value over here. When you have e power negative zeta omega n plus this, so it's actually e power negative zeta omega n multiplied by e power omega n square root 1 minus z square I t. To explain this, just as you learned in math, what we used, if you have e power a plus b, okay, that's equal to e power a multiplied by e power b. Okay, so e here power, those two values summed, it's e power negative zeta omega n, okay, plus multiplied by the second term, e power omega n squared root 1 minus zeta squared I t over here. Okay, so I took this as common factor, e power negative zeta omega n t multiplied by those two terms over here. Okay, now omega n multiplied by square root 1 minus zeta square, we're going to introduce a new parameter. This value, omega n square root 1 minus zeta square, we're going to name this omega d, the damped frequency. Okay, the damped frequency. What is the damped frequency? The damped frequency is the natural frequency multiplied by square root 1 minus zeta square. So u of t is e power negative zeta omega n t. Okay, and we introduced zeta. Okay, we know zeta is, you know, c divided by 2m omega n. Okay, so c divided by 2m omega n, that's the zeta. Okay, it depends on the damping factor, okay, and the mass and the frequency. So e power negative zeta omega n t multiplied by c1 e power I omega dt plus c2 e power negative I omega dt. Okay, this part here, okay, without this initial factor, this is exactly looks the same like the solution that we had for the undamped equation of motion. Okay, and we changed that to a cosine omega nt. Now it's going to be changed to a cosine omega dt. Okay, plus b sine omega dt. Okay, but first, omega d is omega n multiplied by square root 1 minus zeta squared. For zeta, okay, the omega d can have one of three things. If zeta is less than 1, let's look here on this equation. If zeta is less than 1, so zeta squared, let's say zeta is 0.5. So 0.5 squared is 0.25. So 1 minus 0.25 is 0.75. So omega d, okay, will be, you know, a real number. Okay. So if zeta is less than 1, omega d will be real, and the solution will be like this, okay, imaginary. So if you have imaginary exponential functions like this, you can simply remove those two terms and put a cosine omega dt and b sine omega dt as we did with the undamped equation of motion. So u of t now is e power negative zeta omega n t multiplied by a cosine omega dt plus b sine omega dt. Okay, so it's actually u of t. Okay, if zeta is less than 1, we call this underdamped motion. So if zeta is less than 1 for underdamped motion, the displacement will be the multiplication of those two functions. Let's plot those two functions separately. The first one, u of t, is e power negative zeta omega n t. Okay, as t increases, okay, what will happen is the power over here will increase with a negative sign, so it approaches 0. Okay, so if this function, we call this f of t, e power negative zeta omega n t, we termed as, we use f of t of it. So f of t as function of t is a decaying function like this with time. As t increases, it's going to decrease and decrease, and the steady state solution will be 0. Okay, when t becomes infinity, the solution here, or this value, will be 0. What about the second term here, the second function? Let's name this g of t. This is simply exactly the same as the one we plotted before for the undamped equation of motion. It's a cyclic function. It has two harmonic functions with the same frequency, omega d. So the only difference here is the frequency changed. Instead of being omega n, it's omega d, which is omega n multiplied by square root 1 minus zeta squared. Okay, so it's a cyclic function like this. Okay, with a period. The period will be 2 pi divided by omega d. The function, that's the frequency over here, omega d. Okay, so this is g of t, and it's multiplied by this f of t. So how to multiply those two plots together? Simply at each time you multiply this value by the equivalent value over here. So multiplying the two values, it's an oscillating function, but with a decreasing, amplitude. Every time the amplitude decreases. Okay, so this is the envelope of the function over here, e power negative zeta omega n t. It will never decrease or increase beyond this value. You're multiplying this by the decaying function over here. Okay, so this is oscillating, but each time you're multiplying the amplitude by smaller value as you move along that curve over here. So it's the same oscillating function, but with a decaying amplitude each time until at the end it reaches 0. Okay, so that's u of t. So imagine here you apply an initial velocity, initial displacement. Okay, you have an amplitude of oscillation. The frame oscillates, but every time the oscillation decreases until it reaches 0, and that's what you would expect in real life. So now this is, fixed. Okay, this is applicable. This oscillation will happen if zeta is less than 1. We call this an underdamped motion. Okay, if zeta is less than 1, we're going to see if zeta is 1 and zeta is larger than 1, what will happen. But first, before doing this, let's see now. This is the function that we have. Okay, u of t is e power negative zeta omega n t multiplied by a cosine omega dt plus b sine omega dt. Okay, how much is a and b? You would say, okay, we found a and b. A is going to be u naught, right? The initial displacement, and b is going to be u dot naught divided by omega n, as we find for the undamped equation of motion. No, let's apply. We're going to apply the same concept as we did for the undamped vibration, okay, free vibration, but we're going to end up with different values for a and b. So let's try to find the constants a and b over here, okay, for the vibration. So from the boundary conditions, when t is equal to 0, u is going to be u node and u dot node. So and u dot is going to be u dot node. So u node is going to be e power negative zeta omega n power 0, e power negative zeta omega n multiplied by t, which is 0, multiplied by the constant a cosine 0, which is 1. So a is u node. So the same like the undamped motion. But on the other hand, this is u of t now, is e power negative zeta omega n t, a cosine omega dt plus b sine omega dt. The derivative, finding the derivative of this equation with respect to time to find the velocity over here, you're going to have this function multiplied by this. So the derivative will be the derivative of the first function multiplied by this, and then the first function multiplied by the derivative of the second function. When you have two functions multiplied by each other, the derivative is the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. So the derivative of the first one over here is negative zeta omega n multiplied by e bar negative zeta omega n t multiplied by the second function over here plus the first function, what we have over here, multiplied by the derivative of g of t over here. So the derivative of g of t is, as we did earlier, is negative a omega d sine omega dt plus b omega d cosine omega dt. Okay? Now put t equals 0, e bar negative 0 is going to be 1. Okay, so negative zeta omega n a. Okay, so a is u node, and then this term is going to cancel because you have side 0 is 0, and then this becomes 1, and then over here this is 0, and then b omega d cosine 0 is 1, so b omega d. So u dot node is equal to negative zeta omega and u node plus b omega d. So how much is b? You move this term to this side, so u dot node plus zeta omega and u node, and then divide by omega d. So that's the constant over here. So u of t is e bar negative zeta omega n t, a is u node cosine omega dt plus b, which is u dot node plus zeta omega n u node divided by omega d sine omega dt. So this is the equation, the general solution for the free damped equation of motion. Okay, so let's compare the damped solution with the undamped solution. Okay, so the undamped is an oscillation to infinity. Okay, it doesn't, the amplitude here doesn't decrease from one cycle to another. The undamped, the first difference here, okay, it's this term that will cause the amplitude to decrease each time. So each time it's decreasing. The other difference here between the two oscillations, the undamped oscillation had a frequency of omega n. Okay, this one has an oscillation of omega d. The frequency of oscillation is omega d. So omega d and omega n will not have a huge difference in between. Okay, the omega d will be smaller frequency. Okay, so now what if zeta was equal to 1? Okay, if zeta is equal to 1, so omega d is equal to omega n multiplied by 1 minus zeta squared, so 1 minus 1 is 0. So omega d is 0, so u of t is e bar negative zeta omega n t a cosine 0, okay, which is 1 plus b, so actually you end up by a e bar negative zeta omega n t. Okay, what is this? It's only the first term of the function. You don't have oscillation. So for if zeta is equal to 1, this is called critically damped motion, and for critically damped motion there is no oscillation. It's just a decay, okay, an exponential decay of the motion. What if zeta is larger than 1? We call this overdamped motion, and this omega d will be then, if you put zeta here is larger than 1, so this term will be an imaginary number, and imaginary number multiplied by imaginary number over here is going to be a real number here. So what does this mean over here? You're going to still have an exponential decay. So comparing the three cases, if you have zeta that is less than 1, you're going to have an underdamped motion where you have an oscillation like this, okay, a decaying oscillation. But for critically damped and overdamped motions, there is no oscillation. The motion will just decay directly like this, okay, with a faster rate for the overdamped more than the critically damped case, okay. Now the values of zeta, okay, for most buildings, okay, we have zeta is usually less than 0.2, okay. So that's why, okay, if you compare omega d by omega n, if zeta is, let's say, 0.2, okay, omega d is omega n multiplied by square root 1 minus zeta squared. If zeta is 0.2, this is like the average value, okay, or the normal value for normal structures. It's around 0.2, 0.3 maximum, okay. So let's say 0.2. 0.2 squared becomes 0.04. So 1 minus 0.04 is 0.96. Square root 0.96, okay, let's find square root 0.96, it's 0.979, 0.98. So actually the frequency of the vibration, of the damped vibration, although it's different from the undamped vibration, but they are so close to each other, maybe 98%. Okay, so omega D is around 98% of omega N for regular structures, or for most structures. So we're gonna stop here for this video, okay, and then I'm gonna start recording another one here to try to find the decay of motion under for other damped cases, okay.